This lecture is on Chapter 8 of your textbook, Neural Networks and Deep Learning. So today we're looking at neural networks and deep learning, which are some of the most widely used approaches in modern AI. Earlier in the course, we worked with models where features had to be carefully designed by humans, such as the machine learning models that we recently talked about. Neural networks change that. Instead of handcrafting features, the model learns patterns directly from data. These systems are especially powerful for complex, unstructured problems like images, text, and behavior patterns, which make them very relevant to cybersecurity. In cybersecurity, we often deal with patterns that are too complex to capture with simple rules. For example, detecting unusual network behavior, identifying malware, or spotting suspicious login activity across systems. These are not clean, rule-based problems. Neural networks help by learning patterns from large volumes of data instead of relying on predefined rules. That allows them to detect subtle or previously unseen threats. A feed-forward neural network is the simplest type of neural network. You can think of it as layers of processing. Data comes in through the input layer, gets transformed through one or more hidden layers, and then produces an output. Each layer applies a transformation to the data, gradually extracting more useful patterns. The key idea is that the network learns how to transform inputs into outputs by adjusting its internal parameters during training. Now let's look at convolutional neural networks, or CNNs. If we tried to use a basic neural network for images, it would struggle. For example, if you shuffled the pixels in an image, the model would completely fail to recognize it. CNNs solve this by focusing on small local patterns like edges or textures and recognizing them regardless of where they appear in the image. This makes them much more effective for tasks like image recognition and pattern detection. CNNs work because of two key ideas. First is locality. Instead of looking at the entire input at once, the model looks at small neighboring regions. Second is parameter sharing. The same pattern detector is applied across the entire input, which allows the model to recognize the same feature in different locations. Together, these ideas make CNNs efficient and very good at detecting structured patterns. Although CNNs are often associated with images, they're also useful in cybersecurity. For example, malware binaries can be represented as structured data similar to images. Network traffic can also be analyzed as patterns across time or packets. A CNN can learn to recognize patterns associated with specific types of malware, even when the code is modified or obfuscated. This makes them useful for automated threat detection. Not all data is static. In cybersecurity, many problems involve sequences over time. Examples include login attempts, user activity across systems, or event logs from security tools. Sequence models are designed to handle this kind of data. Instead of looking at one event at a time, they learn patterns across a sequence. This is important for detecting things like slow attacks, insider threats, or multi-step intrusions that unfold over time. In cybersecurity, many threats are not single events. They happen as a sequence over time. For example, a series of failed login attempts, followed by a successful login, followed by unusual system activity. Each individual event might not look suspicious, but the sequence tells a story. Sequence models are designed to capture these patterns over time. This allows them to detect slow attacks, insider threats, and multi-step intrusions that would be difficult to catch with simple rules. Transformers are a newer type of model that improved how we handle sequence data. Instead of processing data step by step, transformers can look at an entire sequence at once and determine which parts are most important. They do this using a mechanism called attention, which allows the model to focus on relevant pieces of information and ignore less important parts. This makes them much more effective for large-scale data like text, logs, and event streams. In cybersecurity, transformers are especially useful for analyzing large volumes of text and logs. They can help with tasks like analyzing threat intelligence reports, correlating alerts across systems, and assisting with automated triage. For example, a transformer model might connect multiple alerts that seem unrelated and identify them as part of the same attack. This helps analysts see the bigger picture more quickly. So now we'll talk a little bit about large language models, such as ChatGPT, Gemini, and others and Copilot, Microsoft Copilot, others you'd be familiar with. So, do LLMs understand? Well, large language models can produce very convincing answers, but that does not mean they truly understand what they are saying. And these examples, you can pause here and read these if you like. I mean, they're kind of absurd. And so these examples show that the model can generate confident responses that are completely incorrect or even nonsensical. This is an important limitation. The output can sound fluent and authoritative even when it is wrong. In cybersecurity, this becomes a real risk if analysts trust the output without verification. And it's a huge problem. If you use LLMs much, you have probably noticed the same thing. I get very frustrated when I try to ask a simple question and I'm expecting the LLM to verify information before giving it to me, and it doesn't. It gives me something obviously false. So then I go and research it myself and come back and say that it didn't even research or check, and it admits. It'll say, oh no, I was just, matching patterns and I didn't actually go out and verify the information. So yeah, I've definitely experienced that firsthand with LLMs, as many of you I'm sure have. So now let's talk about LLMs and cybersecurity. So large language models can still be very useful in cybersecurity. They can assist analysts by summarizing alerts, generating reports, and helping with threat hunting. However, they also introduce risks. They can produce incorrect analysis, and there is a tendency for users to trust them too much. They can also be used by attackers for phishing, social engineering, or generating malicious content. So the key idea is that these tools should support human decision-making, not replace it, just support it. And there are also broader concerns with deep learning systems. These models are trained on large data sets, which can include bias and problematic content. That bias can show up in the model's outputs. A trained model is only as good as the data it's trained on. Training these systems also requires significant resources, which means the benefits are concentrated among large organizations. There are also risks related to misinformation, manipulation, and misuse. These are not just technical systems. They have real social and ethical implications. When not to trust AI in cybersecurity. There are situations where you should not rely on AI systems. If the data is incomplete or biased, the model's output may be unreliable. If the cost of being wrong is high, you need additional verification. And if the model cannot explain its reasoning, that limits how much you should trust it. In practice, this means AI should always be combined with human judgment, validation, and cross-checking against known indicators. That's all very important. When I detected the AI was very confidently giving me information that that I doubted the accuracy of, I asked for sources, and it simply said it couldn't find any reliable sources. But I later, then I Googled it and said, well, they were pretty easy for me to find. And it basically admitted at that point, oh, I was just checking patterns, and no, I didn't actually go out and try to verify the information. So just beware when using AI. When used as a collaborative tool combined with human judgment and with validation and cross-checking, it can be very beneficial. But in the wrong hands, with somebody that just gives complete blind trust to whatever the AI says, it can be very damaging. And that concludes chapter 8.